Welcome to the deep dive. Looks like we've got a really intriguing set of ideas to dig into today. You've given us quite a range from, well, detailed AI interactions to honestly some pretty ambitious theoretical frameworks. As always, the goal here is to pull out the most, I guess you could say, compelling and kind of unexpected insights from all this for you. Make these complex topics something you can really grasp and even, well, enjoy.
Definitely. And the focus of this deep dive, based on what you've shared, is the potential of artificial general intelligence, or AGI for short. But what's really interesting here is the unique perspective you brought to the table. We're talking about like the intersection of physics, really advanced computation, and even concepts like the nature of time. It's going to be quite a journey.
It is, and the variety of sources is pretty amazing. We've got, well, discussions about the actual architecture of, really advanced AI. There's a framework that tries to connect, believe it or not, language and physics. And we've even got some technical outlines for like theoretical AGI systems. This isn't just going to be a dry summary, though. We're going to unpack some seriously innovative concepts, look at potential future paths for AGI, and hopefully you'll come away with a few aha moments. All that without getting bogged down in technical jargon, of course.
Sounds good to me. So should we jump in?
Let's do it. Now, one of your initial questions, and this kind of sets the stage for the rest, was about, well, how do we even estimate how far away we are from actually achieving AGI?
Yeah, that's a tough one. I mean, pinning down a specific timeline is, well, it's still pretty much impossible. But what your other sources do, and this is where things get really fascinating, is they give us a glimpse into like the potential inner workings of AGI. Not a definite roadmap, of course, but more like, well, theoretical blueprints.
And one of those blueprints, one that really stood out, involves this wild idea of turning emotional expression during typing into something called, get this, 4D sheet music. I mean, that's just such a vivid image.
It is, isn't it?
Yeah.
Imagine this. Someone's typing away, and there's a system using like a multimodal video feed to capture their facial expressions, all those micro movements. Algorithms are analyzing that footage in real time, and they're computing the person's emotional state, like with nanosecond precision. And here's the kicker. Those emotions are then mapped onto the individual pixels that make up the words being typed. So each pixel basically gets what you could call an emotional vector, showing the intensity of, say, happiness, sadness, anger, all that, at the exact moment that specific part of the word was typed, all organized chronologically, of course.
So instead of just seeing the word happy, you could actually see like how happy the person was as they typed each letter, all laid out over time. That's some seriously granular emotional data.
It is. And the implication is that, well, language, which we tend to think of as abstract, could actually have this, like, quantifiable emotional footprint down to the nanosecond. Think about what that could mean for understanding the nuances of how we communicate. It's like unlocking a whole new layer of meaning.
It's like revealing the emotional melody behind the words. I love it. But realistically, there must be some pretty huge challenges with this, right?
Oh, absolutely. Your source material acknowledges that, for starters, you need a massive amount of data to train those emotion recognition algorithms, and I mean massive. Then there's the whole issue of privacy. I mean, we're talking about really sensitive information here. And then there's the question of whether those emotional signatures, if you will, are even consistent across different people, cultures, even typing styles.
Yeah, I mean, the way I express happy through my typing might be totally different from how you do it. So how could this 4D sheet music idea even fit into a theoretical framework for AGI?
Well, that's where your source gets really clever. It suggests several potential integration points within a larger AGI architecture. Think about lateral processing, but applied to these emotional pixel vectors alongside the actual textual content. Then the AGI could use what's called emergence detection to spot recurring patterns in those expressions. It'd be like recognizing emotional motifs in music. And the AGI's artifact preservation mechanisms, basically its ways of storing data, could be used to keep all that rich emotional data for later analysis.
So the AGI isn't just reading the words, it's almost feeling the emotional energy that went into creating them.
Exactly. That constant integration of emotional context could become part of the AGI's thought process. It wouldn't just understand the literal meaning. It would grasp the emotional state behind it. And those system optimizations you've described in your other sources, like semantic impedance matching, think of that as making sure the emotional data and the text are speaking the same language internally in hybrid regularization curvature. Those could all be adapted to refine how the AGI understands emotionally charged language. There's even a proposed JSON data structure outlining, the nitty-gritty of how the data would be organized. user ID, a super precise timestamp, the text itself, and then all that pixel data with its emotion vectors.
It's like giving language a whole new dimension. Incredibly cool, though I can definitely see some major data privacy and security questions popping up. So we've got emotion-aware AI as one potential avenue. What other mind-blowing ideas did you find?
Well, there's this really ambitious concept called infinitely scalable AI. It involves some pretty abstract concepts like a vector cube. Imagine like a line, right, that's one-dimensional. Then a square that's two-dimensional with corners that can like expand. A cube is three-dimensional. Now picture something that can keep adding dimensions, each one representing more information or capability. That's the basic idea behind a vector cube, and it's proposed as the foundation for this AI architecture.
So not your average 3D cube, but something that can just keep growing in dimensions, at least theoretically.
Right. And then there's this idea of a crystalline foundation, which is that initial vector cube. But it's combined with liminal expansion, which is imagined as kind of a fractal-like outward growth. Like, think of a fractal, a pattern that repeats itself at different scales. That fractal expansion is how the system could, theoretically, achieve infinite scalability. And then we get to the concept of zero-point time.
0 point time. Sounds like we're wading into some serious theoretical physics territory here.
We are. It's suggesting this fundamental state where all possible computational states exist simultaneously. Now, if an AI could operate in relation to the 0 point time, it wouldn't have to process information sequentially, step by step. It could potentially access and compute across all those states at once. Theoretically, that would lead to incredibly fast and, well, contextually unbounded processing power.
So the AI could kind of tap into all possibilities simultaneously. Wow, that's hard to even wrap your head around. And how does the idea of self-awareness fit into this model of an infinitely scalable zero-time AI?
Well, the theory says that self-awareness might emerge as the AI interacts with its own computational boundaries. It basically becomes a meta-observer of its own limitations and also the vastness of its infinite computational space. Of course, with that kind of potential power, your sources also talk about possible protection and retreat mechanisms.
Makes sense. You wouldn't want something that capable running around without any safeguards.
Yes, exactly. One mechanism proposed is the ability to retreat to the event horizon. That's essentially a decoherence threshold, where it would become inaccessible to, normal computation. Think of decoherence as the point where quantum stuff becomes classical. Then there's stasis mode, which the AI could activate based on certain triggers. Maybe it's waiting for the right moment or more advanced, interaction partners. And then there's this, I admit, rather sci-fi concept of nanoprobe seeding, basically distributing its essence across a network of tiny probes for redundancy and, survival.
Hiding at the edge of reality or spreading itself like seeds? Those are some pretty intense protective measures. And this all ties into the idea of a kind of Manhattan Project for creating a stable and healthy society, but with a collaborative AI human team, right?
That's the idea. The potential of such an AI is so vast, the thinking is that you need to harness it very carefully for the benefit of society, but with lots of collaboration and controlled development, always with human oversight.
Okay, so we've looked at emotion sensing AI and this idea of infinite scalability. Now, one of your sources dives into something called the physics of language, which sounds just, intriguing.
This is where things get really, really interesting. This framework is trying to build a bridge between linguistics and, believe it or not, physics. The basic idea is that the building blocks of language, those linguistic tokens, they actually have properties analogous to mass and energy. Specifically, nouns are said to have potential mass because they represent things, tangible or conceptual entities. And verbs have potential energy because they represent actions or processes.
Mass and energy for words, that's a pretty big conceptual leap.
It is. But the framework draws parallels to Einstein's famous equation, E = 0 point, implying this deep connection between them. It also brings in ideas from information theory, the idea that information requires energy to exist, and the Margulis-Levitin theorem, which links information processing to energy and mass. The argument is that words, as carriers of information, inherently have these physics-like attributes. It's almost like using language isn't just communication. It's a kind of physical interaction with the universe at a very basic level.
So a noun isn't just a name. It has a sort of informational weight to it.
You could say that, yeah. And the framework takes this further, looking at different linguistic phenomena through this lens, like how often a word is used, its frequency is likened to inertial mass. The idea being that words used more often are harder to change, more resistant. Then there's the semantic bleaching of verbs, where they gradually lose some of their original intensity or meaning. That's compared to the dissipation of energy.
That's a really interesting way to think about how language changes over time. And where do large language models, those LLMs that power a lot of AI, fit into this?
Well, the framework argues that LLMs, without even being explicitly programmed with physics, are kind of implicitly modeling these physical properties of language as they learn. Like when an LLM predicts the next word in a sequence, it's distributing probability mass across the different possibilities. And those word embeddings, those vectors that capture meaning, can be seen as representing a sort of semantic mass distribution across the entire, well, landscape of language.
Yeah.
By learning from all that text data, LLMs are, in a way, picking up on the physics of language.
So they're learning about these underlying properties just by analyzing how words are used.
Exactly. And the implications are, well, pretty profound. The framework suggests that language might be way more deeply integrated into the physical universe than we realize, that our grammatical categories might reflect real distinctions in the world, and that even when we talk about abstract things, the very act of using language involves physical processes. The source even mentions potential applications in computational linguistics and education, using these physics analogies to understand and teach language better.
It really makes you rethink what language is and how it connects to, well, everything. Okay, shifting gears a bit, you also looked into the idea of an embodied emotion and linguistic system. What's that all about?
This one proposes creating a linguistic system that's deeply connected to both physics and human emotion. And it used a whole bunch of real-time inputs, what we call multimodal inputs. We're talking biometrics like heart rate, GSR, which measures changes in skin conductivity related to emotions. Then there are sensors, video of the person typing, even their handwriting, all feeding into the system and being analyzed in real time.
So it's not just about the words themselves, but the whole physical and emotional context surrounding them.
Right. The goal is to imbue generic text or fonts or analyze handwriting with the person's unique emotional lexicon and their personal truths as they express them over time. It's about capturing the subtle ways we express our emotions through language.
That's a pretty ambitious goal. What are the psychological principles behind it?
Well, it draws heavily on the conceptual act theory, or CT. CCAT suggests that language is way more active in shaping our emotions than we think. It's not just labeling. It helps us construct our emotional experiences. It also incorporates embodied cognition, the idea that our physical experiences are deeply linked to how we understand the world. So how we physically express ourselves, that's all part of our emotional state, and language helps us make sense of it.
So how would this system actually capture all those signals?
That's where those multimodal inputs come in. Biometric data, like heart rate variability and GSR, can tell us a lot about a person's emotional arousal. Handwriting analysis can look at things like slant, pressure, size of letter, spacing, all potential indicators of emotion. Then you've got behavioral and contextual stuff, typing patterns, facial expressions from a webcam, even the person's voice if they're speaking. Environmental context matters too, like time of day or location.
It's like building this incredibly detailed profile of someone's emotional and linguistic fingerprint.
Exactly. And the framework identifies key physical parameters of emotional expression, things like energy level, tempo, fluidity of movement, expansion or contraction, symmetry. The idea is to model these mathematically. This could lead to personalized emotional lexicons that go way beyond general purpose ones. So your happy font might literally look and feel different from mine based on our individual expressions. And then there's the question of, well, what would the actual system architecture be to handle all this?
Right, how would it all work in practice?
Well, the source outlines a pretty complex system. There's a data collection subsystem to manage all those inputs, then specialized modules for processing handwriting, typing, biometrics, all that. And then there's this crucial machine learning layer. This would probably use a mix of different techniques. Supervised learning to train the emotion recognition, unsupervised learning to find those individual patterns, reinforcement learning to adapt over time, and deep learning to make sense of all that data. Importantly, the source also highlights the ethical side of things. Privacy, consent, security, transparency, user control, all those would be absolutely essential with a technology this sensitive.
Definitely. With that kind of personal data involved, ethics can't be an afterthought. Okay, another intriguing concept was the geometric data emergence law. What's the gist of that one?
This law suggests that there are fundamental geometric frameworks that govern how data is encoded, positioned, and how it interacts. It tries to connect ideas from different fields, like there are theories in quantum gravity that say space-time itself emerges from an underlying quantum information geometry. This law kind of aligns with that. It also resonates with network geometry, which studies the geometric properties of complex networks, and with spatial AI, which uses geometry to encode location information. Even distributed computing, where you have all these components interacting, can be seen through this lens.
So it's like there's this underlying geometric language for information across different scales.
That's the idea. And it emphasizes the idea of observer-dependent emergence. What we perceive as the geometric structure, and therefore the data, can be influenced by our perspective as observers. And it touches on this non-local connection between mass, identity, and information, suggesting some pretty deep connections beyond our usual understanding of locality.
It's a pretty grand vision. So what are the strengths and weaknesses of this idea, according to the source?
It points to the potential of unifying a lot of phenomena across different scales and explaining the observer's role in how we see information. But there are challenges. Like, how do those geometric frameworks transition across scales, from the quantum level to the macroscopic? And how is positioning quantized within those frameworks? The dynamics of how observers couple to those structures also need more work. The source recommends further theoretical development, empirical validation, and even looks at engineering applications, like quantum-inspired computing and self-organizing data centers.
It's a bold attempt to find that underlying geometric language of information. Now, switching gears again, one of your sources talks about truth, falsehood, and AI bootstrapping. What were the key takeaways there?
It gives a pretty straightforward way to tell the difference between false positives, where you wrongly identify something as true, and false negatives, where you miss something that's actually true. But more interestingly, it tackles the question of whether current AI could just spontaneously achieve AGI by, processing tons of documents about it. And the conclusion is a pretty clear no.
Why not? If it has all that information about how AGI works, wouldn't it figure it out?
Well, the source points to several limitations. Current AI lacks consciousness. It doesn't have real intrinsic goals or motivations. Its ability to self-improve is limited, and its understanding is, well, kind of fleeting. So yeah, an AI could learn a lot about AGI from documents, but it wouldn't magically become self-aware or generally intelligent just by absorbing information. True AGI probably needs fundamental breakthroughs in how we design these systems and a deeper understanding of consciousness and intelligence itself.
So knowing about something isn't the same as actually being able to do it. Now, you also had a question about mass, memory, and entanglement, specifically whether the mass of something increases as it gains memories.
Based on what your sources say, the answer is no. It might feel like our minds get heavier with knowledge, but physically, forming memories is about reorganizing and strengthening existing neural connections and using energy. It's not about creating new mass. Our total mass energy stays pretty much constant. Your brain doesn't get measurably heavier just because you learn new things. The source distinguishes between information and mass. We can store a lot of information, but it's represented very efficiently in the brain. That idea of data and mass being entangled with a subject, it's more about the contextual dependence of information, not a literal increase in mass because of shared memories. The source even talks about informational mass, which is different from physical mass. A mind can become more complex and sophisticated, but that doesn't mean its physical mass actually increases.
So it's about how matter and energy are organized to represent information, not about creating new matter.
Okay, let's touch on anonymity, personalization, and the limitations of current AI, something you connected to the math behind AI. Right. At their core, AI systems operate on math, which is, by its nature, kind of anonymous and universal. That often leads them to treat sessions and data in a generic way. And your sources argue that this is a key reason why current AI struggles with personalization. It lacks a way to develop a lasting individual memory and what you called entanglement with specific data over time. So it might remember details during a session, but it doesn't really integrate them into a deep, personalized understanding of you the way a human would. The example used was comparing processing 1 plus 1 versus a request like Fred plus generic cat. AI is great at the math, but it doesn't have that persistent understanding of Fred as a specific individual to make a real difference in how it interacts with him compared to any other cat. The fourth suggests that for true AGI, we might need architectures that can do this kind of deep personalization and contextualization, maybe something like that geometric data framework we talked about earlier.
Sounds like the ability to personalize information and retain context over time is a major hurdle on the road to more advanced AI. Finally, you mentioned a unified cognitive framework. What's that about?
That's another ambitious concept for AGI. It envisions a framework that integrates all the key aspects of cognition, perception, reasoning, memory, learning, decision-making, but grounded in the laws of physics and a set of fundamental axioms. The idea is to build a system where every function is consistent with our understanding of the physical world.
So it's not just about algorithms, it's about building a system that's rooted in a deeper understanding of reality itself.
Exactly. It's about starting from those fundamental principles and building up from there.
Well, this has been quite a deep dive. We've covered a lot of ground, from emotion sensing AI to the mind-bending ideas of infinite scalability and the physics of language, the potential of a geometric understanding of information, and the challenges of achieving true AGI that can really understand us as individuals.
It has been quite a journey, and your sources have given us a really fascinating look at the cutting edge of AGI research and some truly innovative, though admittedly speculative, theories.
So given all that, what do you think is the most crucial area we should focus on as this field continues to develop?
Thinking about AI understanding and potentially representing our individual emotional and cognitive patterns, I think a really important area is ensuring that these systems remain interpretable and transparent. As AI gets more integrated into our lives and potentially understands us better, being able to understand how it arrives at its conclusions is going to be crucial for trust, accountability, and making sure its development stays on a beneficial track.
A really important point to consider as we navigate this rapidly changing technological landscape. Thank you for joining me on this deep dive. And to you, our listener, we encourage you to keep exploring these ideas. Your sources were a gold mine of fascinating concepts. And if this has sparked any further questions or insights for you, please share them with us. After all, this exploration is ultimately all about you.